Hello students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering in AB Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to discuss with you reflection coefficient and the transmission coefficient with respect to transmission line. So, before going towards the reflection coefficient definition, just have one brief introduction when the reflection coefficient comes into existence. The reflection coefficient comes into existence only when there exists a reflected wave, and when the reflected wave exists, when our transmission line is not properly terminated. So, what is meant by the properly terminated and not properly terminated? The properly terminated transmission line is that line which is either terminated with its input impedance, either terminated with a characteristic impedance. For in general, we always used to say that a match system, a properly terminated system which is terminated, that means its load impedance is equivalent to its characteristic impedance. That transmission line is said to be properly terminated, and in that transmission line there is no existence of reflected wave and there is no existence of reflection coefficient. And in other case, if the line is not properly terminated, that means the load impedance is not equal to the characteristic impedance, then in that case the reflected wave exists and there will be the existence of reflection coefficient. So, here we have doing that with the analysis in the travelling wave system, which contains two components, one travelling in the z direction, positive z direction, another travelling in the negative z direction. The wave travelling in the positive z direction will always the incident wave, and the wave travelling in the negative z direction will be our reflected wave. And load impedance is equal to the line impedance, line characteristic impedance, then this type of transmission line is said to be properly terminated. And there will be no existence of reflected wave, and the reflection coefficient which is given by the tau should be equal to 0 here. Now, if the load impedance is not equal to the characteristic impedance, then that transmission line is said to be not properly terminated, and in that case there exists a reflected wave, and when there exists a reflected wave, then there will be a reflection coefficient. So, if we say that the minimum value of the reflection coefficient is equal to 0. So, now when there will be no impedance, all the wave is reflected back, that is the worst condition of the reflection. When all the incident wave is reflected back, then in that condition, what is all the incident wave, reflected wave is equivalent to the incident wave in that case, and in denominator also we have the incident, so that will be equal to 1. So, the range of the reflection coefficient is from the 0 to 1. The worst case, when all the incident wave is reflected back, and in that case a reflected wave should be equal to the incident wave, and reflection coefficient is given by reflected upon the incident. So, the complete wave is reflected. So, the incident upon incident we can say, and in that case the reflection coefficient will be equal to 0. So, the range of reflection coefficient will be from 0 to 1, and the reflection coefficient already we have discussed till this is equal to reflected voltage or current upon incident voltage or current, or we can say the reflected wave properties upon the incident wave property. And for the properly terminated wave, this reflection coefficient is equal to 0, and if the wave is if the transmission line is not at all terminated, in that case the reflection coefficient value will be equal to 1. Now, here is one transmission line structure which is having the sending end and this is the receiving end, and I plus voltage, I current is going from sending end to the receiving and I minus from the receiving to the sending end. So, the equation will be like this: V should be equal to V plus e to the power minus gamma z. Gamma is our propagation constant and z is the distance. V minus e to the power plus gamma z. This always contains the propagation constant is always with the negative sign, because there will be reduction as the wave propagates from sending end to the receiving end, and P V plus shows the direction of a wave from the sending end to the receiving end, and V minus shows the direction of a wave from the receiving end to the sending end. And similarly, this is the expression of the current, because we have the transmission line equation both in the terms of voltage and the current, as well as we derive the reflection coefficient in the terms of both voltage and the current. Now, when we write the current in the terms of a voltage, we always write voltage upon the impedance. And what is impedance here? The impedance here is the our characteristic impedance. So, V plus upon Z naught e to the power minus gamma z minus V minus upon Z naught e to the power gamma z. And if we want the voltage at the load impedance, then that will be calculated by substituting Z equal to L. So, by substituting the value Z equal to L, we will able to get the voltage at the load end, which is equal to VL equal to V plus e to the power minus gamma L plus V minus e to the power plus gamma L. Now, if similarly, if want the expression of current at the receiving end, then we have to substitute this Z with L, and this is equal to current at the receiving end is equal to V 1 upon Z naught. We have taken, we can have this V plus e to the power minus gamma z minus 1 upon V minus e to the power gamma z. So, just 1 upon Z naught V plus, in the place of Z we have written L here. This will be the current at the receiving end, and the ratio of the voltage to the current at the receiving end is the load impedance. It will be given by, load impedance is given by VL upon IL, and this is equal to, by just by writing this like this, V plus and e to the power minus gamma L plus V minus e to the power plus gamma L divided by IL. What is IL? Z naught is in the denominator side, that is why it comes on the numerator one, and again V plus e to the power minus gamma L minus V minus e to the power plus gamma L. Now, reflection coefficient is equal to the reflected voltage upon the incident voltage, or reflected current upon the incident current, and tau reflected, V reflected by V incident, and it is represented by tau. Now, ratio of the reflected voltage at the receiving end, this will be, and this will minus 1, e to the power minus 1. So, V to the power plus this will be equal to what? Here we have this one VL upon IL is equal to Z naught V plus e to the power minus gamma L. From this expression basically we used to derive the reflection coefficient. So, if we want, what is the reflected wave here? Reflected one is this one, and this is our incident one. So, the expression is basically what here? This will be the reflected upon the incident. The reflected is V minus e to the power plus gamma L, and this will be incident V plus e to the power minus gamma L. This will be the plus and this will be the minus gamma L. So, how can we get this from this expression? So, we have to divide the expression here. This is the reflected, we have to divide it with the incident one. So, this will be Z naught V plus. So, in the place of V, we can have the 1 because we divide the complete expression with the V plus e to the power minus gamma L. So, plus, when we divide this expression, this can be replaced with the tau, which is our reflection coefficient. So, I am just replacing it that, and again V plus e to the power minus gamma L should be equal to 1 minus tau, because V minus e to the power plus gamma L when divided by V plus e to the power minus gamma L, this will be equal to reflection coefficient, our tau. Now, I am writing here our ZL is equal to Z naught 1 plus tau upon 1 minus tau. This will be equal to ZL. When we do the cross multiplication here, ZL minus ZL tau is equal to Z naught plus Z naught tau. So, we have ZL minus Z naught here is equal to Z naught plus ZL tau. So, what will be the expression of tau here? ZL minus Z naught upon Z naught plus ZL. This will be the same which I have written here, ZL minus Z naught upon ZL plus Z naught. This is the same here. So, for getting now we have received the expression of reflection coefficient in the terms of the load impedance and the characteristic impedance just by dividing the reflected wave upon the incident. So, what is the reflected wave? V minus e to the power plus gamma L divided by V plus e to the power of minus gamma L. This will be the gamma, this will be the plus. Okay? This will be the condition here. This way, from there we will obtain the reflection coefficient, that is equal to ZL minus Z naught upon ZL plus Z naught. Now, comes the transmission coefficient. So, transmission coefficient is the term which is existing in both the properly terminated and the improperly terminated wave, because any wave which is incident has to transmit it. We always give the wave just for the transmission purpose. So, as per the principle of conservation energy, the incident power minus the reflected power, the incident power minus the reflected power will give the transmitted power, and when we found out the expression, we will obtain like this. This is our reflection coefficient and this is our transmission coefficient. We will discuss with the equation of the power later on. Before going through the expression of the power, let us first derive the expression for transmission coefficient, which is our capital T here. So, the transmission coefficient is what? Transmitted voltage or current upon the incident voltage or current. This is our again the transmission line diagram, and the wave is P ref is our reflected power, PTR is our incident power, and PINC is our incident power. Now, for the equation of the travelling wave at the receiving end will be equal to V plus e to the power minus gamma L, which is our transmitting, V minus e to the power gamma L is equal to VTR e to the power minus gamma L. And when we, this is in the terms of a voltage, and when we write in the terms of a current, then it is written as V plus upon Z naught e to the power minus gamma L minus V minus upon Z naught e to the power plus gamma L is equal to VTR upon ZL e to the power minus gamma L. Now, what will we have to do? We have to basically find out the expression of T, that is VTR upon V plus. We have to find out the VTR upon plus. upon V plus. The multiplication of equation 3 by ZL. So, for that purpose what we are going to do first, we will divide this expression, that is equation 3, by the ZL. So, what we are getting, ZL V plus upon Z naught e to the power minus gamma L minus ZL V minus by Z naught e to the power plus gamma L is equal to VTR. When we multiply with ZL, this ZL get cancelled and we have the VTR e to the power minus gamma L. And substitution of the result in equation 2, then we have to substitute this result in equation 2. We have the equation 2 here, because equation 2 in the RHS side contains VTR e to the power minus gamma L, and in equation 3 by multiplying with ZL in the RHS side again we are VTR e to the power minus gamma L. So, we can easily substitute. So, I am writing the equation 2 here after the substitution of the VTR e to the power minus gamma L, and it is written as V plus e to the power minus gamma L plus V minus e to the power gamma L should be equal to what? ZL upon Z naught V plus e to the power minus gamma L minus ZL upon Z naught V minus e to the power plus gamma L. So, what we have to find out here? We have to take the common of V plus e to the power minus gamma L and common of this one. When we take the common of this, we will have the value of V plus in the terms of V minus and V minus in the terms of V plus. So, from this expression, we can have the value of V minus e to the power gamma L in the terms of V plus, and when we substitute that back into the equation 2, we will get the value of VTR upon V plus. So, let us do this. So, what will happen here? When we take the common, what is going to happen here? V plus e to the power minus gamma L. I am taking the common of here in the LHS side. So, what we have? We have 1 plus 1, and here this when it comes on the LHS side, it will be minus ZL upon Z naught is equal to, we take the V minus e to the power plus gamma L common here minus ZL upon Z naught and again the minus 1 here. Okay. So, what will be the expression of this? We have minus ZL upon we have V plus e to the power minus gamma L 1 minus ZL upon Z naught divided by minus ZL upon Z naught minus 1. This will be the expression of V minus e to the power gamma L in the terms of V plus e to the power minus gamma L. Let us substitute this value again in equation 2, and when we substitute this value in again in equation 2, we have come with the expression of VTR upon V plus, and that is given by the expression of 2 ZL upon ZL plus Z naught. If you want, then you are able to do this. You have to just substitute this expression which we are getting in equation 2 and then take the ratio of VTR upon V plus. Now, the power carried by the two waves in the side of the incident and reflected wave is equal to incident, this transmitted one will be always equal to incident, this is the transmitted, and this will be equal to incident minus reflected. This is the expression of the power of the incident wave and this is the expression of the power of the reflected. Incident wave is represented by our V plus e to the power minus. Here we have taken the only the attenuation part, we can have the gamma also. So, V plus e to the power minus gamma L as the incident and V minus e to the power gamma L as the reflected, and we know power is given by V square upon. So, from here we have the expression of the power here, and from this when we take the minus of that, when we do the subtraction of this, we will get the value of the transmitted one. So, by already letting that INR is equal to PTR, but I have already substituted this with a PTR, and as per this when we substitute the values, we have come with the another expression of the T, which is our transmission coefficient, that is equal to ZL upon Z naught 1 minus tau L square, which is our reflection coefficient. Now, let us do one numerical related to the transmission coefficient and the reflection coefficient. Here in the transmission line we have provided with the characteristic impedance that is Z naught, that is equal to 75 plus j 0.01 ohm, and the load impedance, that is our ZL, it is equal to 70 plus j 50 ohm. Now, we have to, before proceeding towards this solution, first of all let us have a look again at the formula of the reflection coefficient and the transmission coefficient. This is our reflection coefficient and this is our transmission coefficient. So, transmission reflection coefficient ZL minus Z naught and ZL plus Z naught. So, when we substitute the value, what is the value of ZL here? ZL is 70 plus j 50 ohm, and by substituting the value and by changing it in the phasor form, we already know we have the result with the in the form of a real and the imaginary one. So, we all know that real part comes here, imaginary part comes here, angle here, and the impedance magnitude comes here. So, from there, from this particular relation we were able to calculate first the expression in the ZL minus Z naught in the phasor form, ZL plus Z naught in the phasor form, and then we get the result. And again we have to transform this into the real and the imaginary part. We will do again use this relation, and real part should be equal to whatever with the magnitude here m cos theta, imaginary m sin theta, and we were able with the to receive this answer. And transmission coefficient VTR upon V plus, which is given by this expression. We have the value of ZL, and so just we have solved it, the same relation, we have changed the real and imaginary part into the phasor form, we have received this result, and again we have changed that into the real and the imaginary component. So, till this in today's lecture, in this lecture we have discussed with the reflection and the transmission coefficient, which is one of the most important parameter related to the transmission line. Without this we can't proceed further. Thank you for attending today's class.